Hey guys, in this video, I'm going to go over leaving groups and how to rank leaving groups, and then also kind of a brief overview of alcohols and the reactions that have to do with them. So the first part of this video has to do with leaving groups. And what this basically is when we have either like an SN1 or SN2 reaction. With SN2, the nucleophile, which in this case is a hydroxide, will go in and attack at the alpha carbon, and it will kick off what we call the leaving group. And in this case, the leaving group is the bromide anion. With SN1, the first kind of step is basically waiting for the leaving group to leave on its own, which again, in this case, would be something like bromine. And we would end up like this, conserving charge. But again, bromine is our leaving group. And so with both of these, we want stable leaving groups, because if it's not stable, then it's really either for SN2 not going to want to get kicked off, or with SN1, it's basically going to be too stubborn to leave because it's so unstable if it leaves, and so it never really will leave. But if we have a better leaving group, it will basically allow these reactions to run faster. And then kind of what describes a good leaving group, and that is kind of something that is stable when it's kicked off. And when it gets kicked off, it will normally take its sigma electrons with it, and so there'll be anions. And so, you'll see your bromine, chlorine, iodide, but you may also see some other potential leaving groups. But the kind of key is that they are stable anions. And you can think back to acidity and basicity trends to kind of help figure out what is more stable if it has the negative charge. And just as a reminder, with the halogens, chlorine is less stable than bromine, is less stable than iodine in their anionic form because of the size difference. And so since iodide is larger than the other two, it is able to spread out the negative charge across a larger area. And so there's not necessarily as much of a buildup of negative charge, because that would create more strain and pressure, and that is not ideal. And so some examples of good leaving groups are as follows. We have the chlorine, bromine, iodide, and then we have the tosylate. And then we also have something like a carboxylate. And as you can kind of notice, each of these are a conjugate base of a strong acid, because remember, with a strong acid, when it gets deprotonated, it's stable in its anionic form. And that's exactly what we want. And so the conjugate base of strong acids will also be good leaving groups, because again, they have stabilization for that negative charge. And so with all of these, if we have our nucleophile come in and attack, this will kind of be what we are left with the kind of this example going to that example going to that, and then that example going to all three of the halogens. So those are some examples of good leaving groups. And these are the cases where SN1 and SN2 will occur. But some examples where they won't occur is if our leaving group would be like a hydroxide or a deprotonated amine, or maybe even a carbon with a negative charge. You'll basically never see the carbon with the negative charge because it is so unstable in that form. It will kind of never even be presented to you at this point. Now, the reason that this is kind of important is because if we have some sort of molecule with an OH, we can't do SN2 on this, because if we have our nucleophile go in and attack, kick off the OH as the leaving group, our resulting structure would be this, with a hydroxide as our leaving group, which is, a very strong base, and so it's going to be a bad leaving group. And then as kind of similar to the fact that good leaving groups are the conjugate base of strong acids, when you have a not stable anion or like a strong base, that will be a bad leaving group. And this kind of brings up the next question of what if we had a bad leaving group, but we want to make it a good leaving group? Because, we need to be able to convert these alcohols into something that we can do an SN2 reaction with. And that kind of is the segue into the alcohol portion of this video. And so I'm going to kind of briefly go over a lot of the alcohol reactions, but just to kind of reiterate, don't forget the 3 ways that we can hydrate alkenes, because when we have alcohol reactions, we need to think about how we get to that alcohol in order to do these reactions, because in synthesis questions, it could come up and you have to know where to put the alcohol in order to kind of end at the right target. But there are kind of 3 reactions that we really will utilize in order to convert an OH leaving group into a good leaving group. And the first 2 are very, very similar. It's just which halogen do you put on instead of the OH. And so we have PBr3 and SOCl2, and those will put on bromine and chlorine respectively. But the importance about these reactions is that these go through SN2-like mechanisms. I'm not going to show the mechanism right here, but they will go through SN2, so there'll be an inversion of the groups. And so when this reacts with PBr3, we put the bromine on a dash. And when this reacts with SOCl2, we put the chlorine on a dash. But we may not always want to invert the stereochemistry, and that is where the tosyl chloride comes in very handy. So in this case, we don't necessarily do SN2 at the chiral center right here. And so all of the chemistry is basically done instead with that oxygen right there. And so that oxygen will basically act as our nucleophile to the tosyl chloride. And when it reacts, it will create an OTS group, a tosylate group, which is a good leaving group. But notice, again, no chemistry is done at the chiral center. And so its chirality and its absolute configuration is kept the same. And so now this opens the door to having a good nucleophile coming in and attacking the tosylate and kicking it off as a stable leaving group, because again, the tosylate is a good leaving group. And so this does not go through an SN2 mechanism at that chiral center. And so we retain the stereochemistry again of that chiral center. And so that's really important because we can kind of control whether we invert the groups or not. And a lot of times, you may have to look maybe 2 or 3 steps in advance to see how many times do I need to invert, because sometimes you want to change the OH to a good leaving group to do an SN2. And in that case, you will switch and then switch back. And so you kind of need to keep track and maybe try to look ahead a little bit to see what you're going to do in order to kind of set it up accordingly. So again, those are kind of the 3 reactions that we will use in order to convert a OH into a good leaving group. And so I kind of have a few miscellaneous reactions of alcohols just because I wasn't really sure where to put them. But the first is a dehydration reaction. And basically kind of what I was saying here is don't forget the 3 ways to hydrate, which is to add an OH to an alkene. A dehydration reaction will basically take off an OH and put an alkene in its place. And so it's just the opposite. And so with the dehydration reactions, it is basically an E1 mechanism because the OH will become protonated. Oh, this actually would have been a good one to mention as a good leaving group, because now when this molecule leaves, or when that, water molecule leaves, it is stable because it's a neutral species now once it leaves. So or positively charged species could be good leaving groups, depending, but in this case, and then we will have an elimination. Well, we could probably use the same water molecule, but so in order to get rid of that carbocation, we will take off a hydrogen and end at that product right there. And then the next mechanism, or the next reaction, is basically just adding in HBr to OH or maybe HCl. And it kind of goes through the similar thing where it will basically become protonated and then leave, and then the bromine will attack in this case. So this is a substitution reaction, whereas the one before was more of an elimination reaction. And that does create a chiral center, and so we would want to show both of the options. And then finally, kind of the last reaction that I could find is a alcohol reaction with sodium metal. And what that basically will do is the sodium will rip off that hydrogen and it will kind of bubble out as hydrogen gas. But what's left is the alkoxide anion with the sodium counterion. And this basically opens the door for SN2. And Williamson ether synthesis. And so you may have seen potentially with the halohydrin reactions, let's do this, or you will see, I'm sorry, if you have Br2 and H2O, you will get a product like this. And if you use sodium metal, what will happen is you will deprotonate that oxygen. And then it can basically, through an intramolecular reaction, it will attack this position and kick off that bromine because it is a good leaving group. And it will form a cyclical structure called an epoxide. And so that's one way that we can generate epoxides. And there are others, but that, is just one way that we can use sodium metal as a demonstration. And then another kind of set of reactions is the oxidation and reduction with alcohols. And so there are kind of two major groups. We have the PCC group and the chromic acid and chromic kind of derivative group. And so the PCC will basically oxidize the alcohol one step. And this is really kind of only important with primary alcohols, because with secondary alcohols, we'll see basically one step is as far as it can go. But with primary alcohols, we can oxidize it kind of one step. And then with the chromic acids, we can take it to the kind of final step. And so when we oxidize the primary alcohol, one step will be the aldehyde. And then if we oxidize a primary alcohol with chromic acid, we will get a carboxylic acid. And so the kind of mnemonic that I like to use is chromic completely, and then carboxylic acid. So chromic acid will completely oxidize the primary alcohol and take it to the carboxylic acid. And then just as kind of like a little tidbit of information, PCC and chromic acid are very similar, but the only difference is that chromic acid is basically aqueous. And so if you were to have PCC and maybe introduce it to water, you would end up with chromic acid. And so if you do use PCC, you need to make sure that you do it in a very dry environment, or else the PCC in water will basically turn into chromic acid and then will oxidize to the carboxylic acid. And if you're expecting an aldehyde, but you accidentally have water in the reaction vessel and it turns all the way to the carboxylic acid, that is kind of something important that you may want to hopefully watch out for. And then, so again, those are just kind of with primary alcohols. But with secondary alcohols, if we oxidize it one step, it will oxidize it basically all that it can. And that will basically just oxidize it to the ketone. And so if we have this kind of same secondary alcohol, whether we expose it to PCC or chromic acid, it will have the same final result. Because again, we can't oxidize this any further. Whereas with this, we could oxidize it further. So this kind of may help. So if we have PCC and we have a primary alcohol, we will oxidize to the aldehyde. Secondary alcohol in the introduction to PCC will go to the ketone. Primary alcohol with a chromic acid derivative will go to carboxylic acid. And the secondary alcohol, same thing with the chromic acid, will go to the ketone. So those are kind of the oxidation reactions. And then as the flip side of the coin, we have our reduction reactions. And I'm not sure whether you guys will be tested on this depending on your professor. But if we have a ketone, we can reduce it with hydrogen gas and a platinum, palladium, or nickel and get it back to that alcohol. And if we have an aldehyde, we can also get it back to the alcohol pre-oxidation. But if we go all the way to the carboxylic acid, we basically have crossed over a line that these hydrogenation conditions will not let us return from, because this oxygen has resonance and we can't really kind of disturb that with just hydrogen. And so this kind of will have no reaction. You guys may learn in Orgo 2 of ways that you can reduce carboxylic acids, but under kind of the conditions we know with hydrogenation, it will not happen, reducing carboxylic acids with hydrogen gas. So that is all I have for this video. I hope it was helpful. If you have any questions about this, feel free to reach out on Piazza or GroupMe. Just let me know. Have a good one.